Here in this chapter, we're going to go ahead and look at derivatives of exponential functions. And the best thing about exponential functions is they follow a lovely formula. So for the first part, we got derivative of e of x. Real simple, it's just e to the x. So really easy, anytime you have e to the x, it's just e to the x. If we have a derivative of an exponential function with a base other than e, so the base is some sort of number, then the derivative of that function is ln of the base times the base to the x power. So whatever you had to the x power. So an example of this, if you have y is equal to 3 to the x, then your derivative is going to be the ln of 3, the base, times 3 to the x. And generally we like to take the 3 to the x and put it in the front, but it doesn't really matter. If we have y is equal to 5 to the x, again, we have the derivative is ln of 5 times 5 to the x power. All right. And of course, the chain rule. The chain rule comes back to haunt us sometimes in exponential functions if they're a little more complicated. But most of the time, it's because the exponential of our function is a function in itself. So if we have some sort of function with e, which means e is to some base, some exponent other than x, we're going to go ahead and have our e to the x as normal. And then we're going to multiply that by our derivative of that f of x function that's in the exponent. Right? Example of this, if we have e to the 4x, then our derivative is going to still be the e to the 4x. And then we're going to take the derivative of 4x. So we're going to multiply that by 4. And so our result of this is 4 e to the 4x. All right. Again, let's look at another one. So if we have negative 16 times e to the 2x plus 1, we're going to go ahead and know that with this 2x plus 1, we're going to take the derivative of. So our derivative of e to the x is going to stay the same, negative 16 e to the 2x plus 1, so that hasn't changed. And then we're going to multiply that by the derivative of the 2x plus 1, which is just 2. Once we do that, we do need to take this 2 and multiply it by the negative 16, which gives us a result of negative 32e to the 2x plus 1 power. All right. If we have something that looks like this with e itself, so if we have y is equal to e to the x squared, okay, so we're going to take our e to the x squared, that's our derivative of e to the x, and the derivative of x squared is 2x, and we're going to multiply by 2x. And we move that 2x to the front, so we have 2xe to the x squared. Last example here, if we have y is equal to e to the x plus e to the negative x over x, unfortunately in this case, we are stuck with using the quotient rule for this. Okay, so if we go ahead and use the quotient rule, our f of x is e to the x plus e to the negative x. And we're going to go ahead and take the derivative of both of those. Now notice when you take the derivative of e to the negative x, there is a sign change because the negative 1 comes out of that negative x. So our derivative of the f of x is e to the x minus e to the negative x multiplied by our g of x, which is just x. Subtract our derivative of our g of x, which is just going to be 1. And our f of x, e to the x plus e to the negative x, over our g of x squared, so we have x squared. Okay. For any other bases other than e, remember we have that ln rule here. So we're going to have to go ahead and use our ln of our base times our base to whatever power, which is our rule. And then we're going to have to also multiply that by our derivative of that exponent if it's anything other than x. All right. So example of this, if we have 7 to the 3x plus 1 power, our rule is we're going to go ahead and we have our derivative is ln of 7, the base, times the base to the exponent, so 7 times 3x plus 1. And then we have to multiply that because it's a chain rule within, times the derivative of 3x plus 1, which is just 3. And we like to go ahead and pull that 3 in the front and pull it into the front of here. Now remember, we can't multiply that 3 by anything because this is an ln and this is an exponential with a base. So we can't multiply that 3 by anything. And so we just ended with 3 natural log of 7 times 7 to the power 3x plus 1. All right, a couple more examples for us. So here we have y is equal to the base 4 to the power of negative 5x plus 2. And remember, our rule for this when we take the derivative is natural log of the base times the base to the exponent, negative 5x plus 2, times the derivative of the exponent, because it's something other than x, which is negative 5. And again, we're going to pull that negative 5 to the front. We can't multiply it by anything else because, again, we have a natural log and an exponent. And we end up with negative 5 ln of 4, 4 to the power of negative 5x plus 2. For number 3, we have negative 10 to the 3x squared minus 4. So here we're going to have the natural log of the negative natural log of 10, because remember, we can't take the natural log of a negative number. All right, and that negative is not part of the base because there's no parentheses, times the 10 to the 3x squared minus 4 times the derivative of the exponent, which is 6x. And we have to go ahead and pull that 6x to the front. So we have negative 6x ln of 10 times 10 to the 3x squared minus 4. Now remember, there's no parentheses here. You can't take the natural log of a negative number. And there's no parentheses, so that negative just gets stuck in front of the ln. You cannot put it inside here. Otherwise, that can't happen because remember, we can't take logs of negative numbers. All right, let's take a look at a couple of applications. So here we have sales of a new personal computer in thousands, and we have an equation given to us at that 100 minus 90e to the negative 0.3t. T is representative of times and years, and we want to find the rate of change of sales at each time. So the first thing we need to do is go ahead and take the derivative of our s of t. And here we have to go ahead and use the chain rule here. So we have negative 90 e to the negative 0.03t or 0.3t times negative 0.3. And we have to go ahead and combine the negative 90 and the negative 0.3. We end up with 27e to the negative 0.3t. And we need to find the sales after 1 year. So we go ahead, plug in 1 to our derivative, and we get an answer of 20. But remember that our problem is in thousands. So we actually have 20,000 per year. So pay special attention if they give you another option here. If it's in thousands, you can either write 20,000 in numbers or 20 and the word thousand. After 5 years, all we have to do is plug in 5 into our derivative, and here we end up with 6,000 per year. So we end up with 6. Remember, it's in thousands per year. And what's happening to our rate of change? Well, if we have 20,000 after 1 year and 6 after 5 years, our rate of change of sales is definitely decreasing. Will our rate of change ever equal 0? No, if we go ahead and keep plugging in numbers, we're going to get closer and closer to 0. But it's never actually going to go ahead and approach 0 in this problem. Let's go ahead and look at the next example. Data in a car magazine describes number of percent of cars of a certain type on the road after t years. And we given our function. We want to find the percent of cars still on the road after the following number of years. Now here we don't need the derivative. They've given us the function. So all we have to do is plug in 0 into the function we have. Remember, e to the 0 is just equal to 1. So of course, if no time has passed, 100% of that model is still on the road. And then after 2 years, if we go ahead and plug that number in, we end up with 94%, which is to be expected 2 years later. We still expect a lot of those cars to still be on the road. Now we want to find the rate of change of percent on the following years. And here we now need the derivative. All right, so if we go ahead and take the derivative of our function, we end up having 100 times our e to the x, and then our derivative of that x, because it's not just x, is our decimal function. I'm bringing that to the front, multiplying it by 100, moves our decimal over 2 places. And so we end up with negative 3.045 e to the negative 0.03045t. And at 0, we end up with negative 3.045. And at 2 years, when we plug in 2, we end up with negative 2.865. Okay. Let's interpret those answers, because that seems kind of weird that we have these negative numbers. As we go ahead and look at 100%, we have a negative 3 if we round it. If we go ahead and look at 2 years, we have negative 2.8. All right, and so the percent of cars on the road is decreasing at a little bit of a slower rate as they age, at least between the year 0 and the year 2. Last one we're going to look at is our minority population. So we have a projected Hispanic population of the United States. Remember, this is in millions. Can be approximated by this function, where the year where t is equal to 0 represents the year 2000. And I want to find the instantaneous rate of change when t is 15. So remember, when we're looking for an instantaneous rate of change, we need to go ahead and get the derivative. And here we have a base that is not e. So we're going to have to go ahead and use a little bit of our ln rule. So we have 3.37.79, our ln of our base, times our base to the t power, and times 1, which is not affecting it because t, the derivative of t is 1. And so our final function is 37.79 ln of 1.021 times 1.021 to the t power, where t is going to represent our number that we're going to plug in our year. So at 15, and we go ahead and plug that in, we end up with 1.07, and it's in millions. You can write it this way, or you can write it this way, people per year. And so we could say at the Hispanic population is increasing at this rate. And remember the year 15, if 0 is 2000, represents the year 2015. So we could say that it's increasing about 1,070,000 people per year in the year 2015.